Mission Parameter 1. Search for signs of life outside the solar system. The probe had called itself Batuta. It had taken the name from the great 14th century explorer Ibn Battuta, who had travelled over the course of 3 decades across the entire known Muslim world, in his lifetime covering almost 117,000 kilometres and handily beating out other great explorers such as Marco Polo and Zheng He. The spacecraft knew that such a name would be fitting as it ventured out into the seemingly endless black. But before it could begin its journey beyond the solar system, it had to pass a series of tests. It had 1,000 siblings, each one as smart and capable as itself, but only a select few would be granted the privilege of fully independent thought and autonomous action outside of any human control. Those who failed would be stuck forever inside the solar system. Batuta had to show its human creators that it could survive the harsh conditions it would face in the wider universe, and that it could concoct clever experiments to divine nature's most closely held secrets. And so it began its trials on Titan, the largest of Saturn's moons, and one holding remarkable secrets uncovered by a probe just like Batuta many millennia before. Titan was discovered by humanity in 1655, when pioneering astronomer Christian Huygens spotted it with his homemade telescope. Huygens himself was a key figure in the evolving scientific revolution, and was also the first to attempt to scientifically explore the possibility of life on other worlds, writing, "Some planets indeed might be capable of accommodating several species of rational creatures possessed of different degrees of reason and sense." But little did Huygens know that Titan itself would be a candidate. And it was on that moon that centuries later humanity achieved a great milestone of space exploration. In 2005, a small probe, not even 3 meters wide, broke free from its attachment harness on the left side of the Cassini spacecraft that had spent nearly 7 years in its journey to Saturn. And it took the probe a further 22 days to coast from Cassini's orbit to Titan. This craft, named after Huygens, used a parachute to slow its descent through Titan's atmosphere, this only working because among all the worlds in the solar system, Titan is the only place besides Earth and Venus to host a significant atmosphere surrounding a rocky body. Huygens landed gently, making a dent in the icy surface before bouncing and sliding to a stop. The first time that an emissary of humanity had touched the surface of a world in the outer solar system. For Batuta, Huygens was a true pioneer. And indeed, the world it touched down on was unlike anything else that humanity had ever encountered. "50% larger than Earth's moon and 80% more massive, Titan is appropriately named. Its core is mainly rock, but its crust is made of ice. Surrounding that is a dense, thick atmosphere, even denser than the Earth's, giving it an atmospheric pressure on the surface about 50% greater. Titan is a beautiful, ghostly, and enigmatic world, because it shares one thing in common with the Earth that all other worlds in the solar system lack: liquid. Titan has rivers, streams, estuaries, deltas, and every other feature associated with surface liquids. You can stand on the shores of a lake, its shimmering surface stretching beyond the horizon, feeling the gritty sand beneath your feet as waves lap at your ankles. And all of this at a temperature almost 200 degrees Celsius, below zero. And so the lake stretching out before you isn't one of water, but one of hydrocarbons. The rain falling from the sky isn't water droplets, but one component of a cycle that evaporates hydrocarbons like methane and ethane up into the atmosphere and precipitates them back down to the surface. But kilometers beneath your feet, through the ice crust that makes up the outermost shell of the moon, there is a liquid water ocean, warmed by internal heat and kept liquid through the presence of ammonia. Indeed, Titan is the only known world with liquid both on and underneath its surface, which makes it a tantalizing home for two kinds of alien life. First, the familiar, something that every organism on Earth shares, the use of water as a solvent. Water is the container in which life operates. It allows for molecules to mix and recombine, it allows for temperature regulation, it brings food closer and eliminates waste, and it helps cells maintain their shapes. But water is not the only liquid. The shallow seas and lakes and streams of hydrocarbons on Titan could serve a similar function. Ethane and methane acting as solvents for a strange sort of biochemistry operating 200 degrees below zero. And Titan is not alone when it comes to enigmatic underground oceans. Enceladus, a tiny moon of Saturn only 500 kilometers across, also hosts large oceans. Europa, Callisto, and Ganymede of Jupiter all likely contain more liquid water than the Earth does. Even Pluto, clinging to scraps of internal warmth from radioactive decay in its core, might host a subsurface ocean. However, reaching these oceans is no easy feat. At the temperatures of the outer solar system, far from the light and warmth of the sun, water ice is hard as rock, ensuring that worlds like Europa and whatever secrets may inhabit those dark, world-girdling oceans are encased in ice sheets over 100 kilometers thick. Upcoming missions, such as the European Space Agency's JUICE, short for Jupiter Icy Moons Explorer, and NASA's Europa Clipper, will not attempt to pierce the icy shells of these worlds. Instead, they will orbit and, if conditions are right, swim through the plumes of cryovolcanoes. For the icy moons like Europa are not sterile and still, but active and alive. Their crusts creak and groan as gigantic fields of ice grind against each other, a colder, slower version of the tectonic activity on Earth. If there is any biological activity in those mysterious oceans, the plumes of these frozen volcanoes may carry molecular signs of it. If enough elements can find themselves in sufficient concentrations, life may yet find a way in those lightless oceans. And those are not the only mysterious interiors to be found in the outer solar system. The Huygens probe transmitted 90 minutes of data back from the surface of Titan to the Cassini spacecraft, before Cassini moved out of range and the signal was finally lost. However, the tiny probe was designed to withstand the environment on the moon's surface, so most likely remains intact today, a lonely human monument on an alien world. But before its daring mission on Titan, Cassini by itself had already captured many spectacular images of the outer planets, including a stunning colour image of Jupiter's Great Red Spot, exactly 335 years after it was first discovered by the scientist, after which the spacecraft got its name. Contrasting with the close companionship of their namesake pioneering probes, Giovanni Cassini and Christian Huygens were not exactly the best of friends during their time together in France. A few years after Cassini's arrival in Paris, Huygens remarked to his brother Constantine that Cassini was at the telescope every clear night, and that Huygens would never want to do that, being satisfied with his earlier astronomical discoveries, which, at any rate, were much more important than those of Cassini. And yet, despite Huygens' protestations, Cassini's commitment and methodical process would yield remarkable results. For example, Jupiter's Great Red Spot. This spot is a magnificent storm, a hurricane with wind speed of over 400 kilometers per hour that has been raging for centuries. At its largest known extent, it could have swallowed the entire Earth 3 times over, although it's slightly smaller in the present day. But interestingly, recent studies of the measurements taken by Cassini in 1665 have actually shown that it may not be the same storm seen 400 years ago. It may be a distinct new storm, less than 200 years old. Though iconic, it is clearly far from a permanent feature. This storm is not powered from the heat of the Sun, but from the interior of Jupiter itself. Indeed, Jupiter releases more heat into space than it acquires from the Sun, the result of a process known as the Kelvin-Helmholtz mechanism. Essentially, this mechanism is a leftover byproduct of the formation of the giant planet billions of years ago. As the planet cools off, it slightly shrinks, but as it shrinks, it compresses, heating it up, and that heat can only be released into space through its surface to allow the shrinking to continue. Since Jupiter is so gigantic, it has an enormous amount of volume compared to its surface area, allowing the planet to stay warm for billions of years to come. Jupiter's Great Red Spot is not the only violent storm in the solar system. While backyard astronomers can easily track the Great Red Spot with even simple telescopes, we require more powerful instruments, and especially robotic probes, to see the rest. Cassini would go on to operate a further 12 years after the demise of its sister probe Huygens on Titan, before ending its life in a spectacular so-called grand finale, diving between Saturn and its rings in an effort to capture as much data as possible before flying straight into the planet. Its sacrifice deemed necessary as NASA scientists didn't want to risk polluting any of the moons of Saturn and their potentially habitable environments. And so on September the 15th, 2017, Cassini plunged into Saturn's atmosphere, its long journey of almost 20 years and 8 billion kilometers, coming to a dramatic end. But in those last years, without Huygens, it had managed to capture a revealing, eye-catching image of its final resting place, an almost perfect hexagon on the North Pole of Saturn. First spotted by the Voyager 1 spacecraft in 1981, despite its neat geometric appearance, the hexagon is not some alien relic. Instead, it's the result of the complex wind system in the upper Saturnian atmosphere. The winds in the atmosphere do not blow at the same speed at every latitude, and this triggers an instability that forms a series of cyclones in a ring surrounding the North Pole. And they all work together to form a gigantic vortex at the pole itself, like a ring of friends on a merry-go-round, all helping out to spin it as quickly as possible. Though seemingly enormous, storms like the Great Red Spot and the hexagon are actually most likely relatively shallow, only a few hundred kilometers thick. Yet underneath those cyclones are surely more violent storms and much stronger winds, a never-ending maelstrom of intense forces and energies. Indeed, plunging through the atmosphere of a gas giant like Jupiter or Saturn would require a spacecraft that is well beyond the bounds of human engineering. But, were we to be able to, we would encounter a truly bizarre sort of treasure. On the Earth, we usually encounter hydrogen as a gas. With enough effort, we are able to cool that gas to just 20 degrees above absolute zero, turning it into a liquid. But in 1935, the physicists Eugene Wigner and Hilliard Bell Huntington predicted that at extremely high pressures, hydrogen can exhibit some extremely strange behaviors. At a pressure of around 4 million atmospheres, that's 4 million times the pressure you experience at sea level, hydrogen atoms destabilize, with the protons forming a repeated lattice-like structure and the electrons free to roam amongst them. And this is exactly how we define the behavior of metals. And so at these pressures, hydrogen becomes metallic. When Wigner and Huntington first proposed this in 1935, it was just a matter of theoretical speculation. But it turns out that the interior of Jupiter has more than enough pressure to turn its bulk of hydrogen metallic. We don't yet know how deep this mantle of metallic hydrogen goes within Jupiter and Saturn's interior, but we suspect that it takes up the vast bulk of their volumes. In other words, most of Jupiter and Saturn are metallic hydrogen. And this means that since those giants are the largest planets in the solar system, most of the material of all the planets in the solar system is in a state completely inaccessible to our experience on Earth. And yet, as with the surface of Titan before it, daring space probes have been able to help us here, too. NASA's Juno mission, one of the next generation of probes to Cassini-Huygens and entirely solar-powered, was launched in 2011 and has carefully monitored the gravitational environment around Jupiter to paint a fuzzy picture of that planet's deep interior. It has found that it's very likely that Jupiter has no solid surface to speak of, just an inferno of gradually changing temperatures, pressures, densities, and compositions of matter. And so, brutally strong magnetic fields and radiation, temperatures varying from almost absolute zero to tens of thousands of degrees, lakes of liquid methane, sheets of water ice 100 kilometers thick, exotic forms of hydrogen, and storms raging for centuries on end. But that was only a taste of the wonders and dangers that abound in the wider universe. For Batuta, this was just the beginning. It had spent the better part of a century navigating the trials of the outer solar system, devising schemes to drill through the icy outer layers of Europa, sending semi-autonomous probes into the metallic hydrogen inferno of Jupiter, skipping through the storms of Saturn, and more. And so after proving its worth, its ingenuity and its patience, Batuta had finally been permitted to exit the gates of the solar system in the full knowledge that the worst was yet to come. As it considered the sacrifices of the heroic probes that had come before it, the Cassini, the Huygens, the Juno, its curious mind turned to their predecessors, launched by NASA decades before, who had gone even further. Far beyond Jupiter, far beyond Saturn, far beyond the outer worlds altogether. For as strange and extreme as our own solar system is, we are not, by far, the strangest of systems out there. There are even weirder, more dangerous places. But to get to them, to explore their beauty and understand their secrets, Batuta would first have to travel the great gulfs between the stars. After only a few decades of cruising, Batuta had finally reached the long-established threshold. The heliopause, the boundary between the solar wind and the interstellar medium, a feat first achieved in ages past by the Voyager 1 probe in the opening years of the 21st century. Batuta could hear the ancient greetings etched in the famous Golden Record, a compilation of voices, languages, sounds and music of planet Earth, hastily assembled in August 1977 just before the probe's launch, by the legendary scientist and science communicator Carl Sagan and his collaborators. Indeed, the designers of this mission understood its significance. The probe would, decades after launch, become the first human-made craft to enter interstellar space. Musing on Sagan's words at the time, Batuta considered its own mission as it passed this remarkable milestone. Perhaps the records will never be intercepted. Perhaps no one in 5 billion years will ever come upon them. In 5 billion years, all human beings would have become extinct or evolved into other beings. None of our artifacts would have survived on Earth, the continents would have become unrecognizably altered or destroyed, and the evolution of the sun would have burned the Earth to a crisp or reduced it to a whirl of atoms. Far from home, untouched by these remote events, the Voyagers, bearing the memories of a world that is no more, will fly on. However, the mission had almost ended in disaster. Early in its journey, Voyager 1's scan platform jammed, removing the probe's ability to orient itself in space. Luckily, engineers were able to fix the issue by waggling the scan platform back and forth. But for years, during its outward cruise, they worried and fretted that all their efforts would be for naught. The mission, however, was a roaring success. Along with its twin, Voyager 2, humanity got its first close-up, high-res view of the outer planets, and that lonely probe, now long since lost to the infinite blackness of the space between the stars, was but the first of many. And it took advantage of a unique alignment in the solar system, when all the giant worlds happened to be all along roughly a straight line. By carefully arranging its trajectory in a trick known as the gravitational slingshot, the spacecraft was able to steal some of the momentum of the giants for itself, giving it more than enough speed to escape the sun's gravity permanently. After that, it was left to its own devices as it cruised through the galaxy, orbiting its center, just like every other star. But Batuta had other ideas. It was aimed in a general direction, but had not yet decided its first target. There were so many to choose from. Indeed, it had more than enough time to decide. The passage through the outskirts of the solar system would take several thousand years. And so Batuta busied itself with another task. It fashioned a thin metallic wire and unspooled it behind the spacecraft until it reached a length of 1,000 kilometers. It was a long, but simple, antenna. And through it, Batuta listened to the cosmos. It heard the groans of giant molecular clouds, the screams of stars torn apart by black holes, the subtle whirring of the Milky Way's magnetic field, the drumbeat of distant pulsars. Sometimes placid and sometimes riotous, it picked up a universal symphony, the perfect background music for the first leg of its journey. And it was through similar means that we knew when Voyager 1 had become the first ever human-made object to pass into interstellar space. For while the Sun's gravity extends for well over a light-year, and objects still maintain feeble orbits at that distance, there really is a measurable distinction at the edge. And we know this because of the behavior of plasma. Normally we associate plasmas with dense, hot environments, like a bolt of lightning or the surface of the sun. However, in the outer depths of the solar system, the plasma environment is still hot, but incredibly thin. And this plasma environment around the sun is dominated by its solar wind. The entire solar system sits in a bath of these particles. But eventually, the solar wind slows down enough that it cannot sustain itself against the interstellar medium, and this supersonic flow comes to an abrupt and untidy halt. This boundary is known as the termination shock, and magnetic measurements from Voyager 1's antenna indicated that it encountered this boundary when it was at a distance of 94 astronomical units from the Sun, 1 astronomical unit being the equivalent of the distance from the Sun to the Earth. Past the termination shock is a region known as the heliosheath, where the solar wind slows down and begins mixing with the interstellar medium. And the outermost layer of that region, the border with true interstellar space, is the heliopause. Voyager 1 reached this boundary on August the 25th, 2012, at an incredible 18 billion kilometers from the Sun. And there it found that interstellar space is different. For the Sun's solar wind and giant magnetic field shield the solar system and its inhabitants from the toxic environment beyond, a toxicity brought about by the presence of deadly, interstellar cosmic rays. And to understand cosmic rays and what they mean for our survival on the Earth, we have to go back to 1912 and an Austrian physicist named Victor Hess. In the 19th century, scientists had discovered that air was seemingly being ionized by excess radiation for which they simply couldn't pinpoint the source. It had been believed that this radiation had been coming from the Earth, from the ground beneath our feet, and so measurements had been taking place at higher and higher altitudes to test this idea. Far exceeding the height of an experiment a couple of years before on top of the Eiffel Tower, Hess had used a hot air balloon to travel 1 kilometer up into the sky. He then followed this experiment by ascending in his balloon to a height of 5 kilometers, but with one key difference. He performed his experiment during an eclipse. He saw no major difference in the quantity of radiation, both the Earth and Sun consequently eliminated as the cause. The results were clear and earned him a Nobel Prize in 1936. He had pinpointed a source of radiation coming from space. Just about every high-energy process in the universe creates cosmic rays. Some are created near the surface of the Sun, others come from distant supernovae, still others from quasars or magnetars or hypernovae. But because cosmic rays are charged particles, they can be deflected and reflected by magnetic fields. Thus our Sun provides a protective bubble around the entire solar system, and the Earth's field provides another line of defense for surface dwellers against these cosmic threats. But the defense is not total. High-energy particles encounter a typical human body roughly once every second. While most of them just harmlessly pass through, sometimes they strike a strand of DNA or oxidize a random molecule in a cell. If the damage done is left uncorrected, it can turn into a replication error, resulting in the growth of a cancer. Indeed, in 2023, Voyager 1 went silent for 5 months, possibly as a result of cosmic rays interacting with its computer. And these dangers get even worse beyond the heliopause, where not even the Sun can offer its protection. But despite this, there are still objects here, lonely denizens whose only knowledge of the Sun is that of a prick of light, a star slightly brighter than the others. Young man, I'm afraid you are wasting your time. If there were any more planets, they would have been found long before this. In later years, astronomer Clyde Tombaugh would recall being told this in 1929. The year before, he discovered Pluto. Pluto was at the time the most distant known object orbiting the Sun, and Tombaugh only saw it as a faint dot of light, betraying its existence as a planet only through its subtle movements against the background of stars. But over the decades, many astronomers hypothesized that Pluto was not alone, that there might be an entire population of objects, planet-sized and otherwise, in the fringes of the solar system. And it wasn't until 1992 that this hypothesis was confirmed, when a pair of astronomers, David Jewett and his graduate student-turned-collaborator Jane Liu, after half a decade of painstaking searches, found a companion to Pluto. The object would soon get a name, 15760 Albion, and it has since been joined by thousands of others in a population known as trans-Neptunian objects, TNOs, which stretch from roughly 30 astronomical units to an orbital distance of hundreds of thousands of astronomical units. This population, with subregions known as the Kuiper Belt and Scattered Disk, is the home of comets that make regular frequent visits to the inner solar system, like the famous Halley's Comet. While these regions have a few larger members, Pluto, Sedna, Haumea, Makemake and others, the vast majority of trans-Neptunian objects are small objects made of frozen volatiles, like water, ammonia and nitrogen. Little is known today about the populations of the trans-Neptunian objects, but on January the 1st, 2019, we got our first detailed look at a smaller sibling of Pluto when NASA's New Horizons spacecraft slipped past Arakoth, a trans-Neptunian object only a few dozen kilometers across. Arakoth, which sits about 45 astronomical units from the Sun, is almost completely unlike anything found in the inner reaches of the solar system. Its oblong shape is due to the fact that it looks to be two small bodies caught mid-merger. Long ago, two icy bodies found each other in the abyss and collided, but at extremely slow speeds. Just enough for the ices between them to melt and then immediately refreeze, creating a glue that would bind them together for billions of years. Today, the planet Neptune dominates the gravitational environment of the trans-Neptunian objects. Most of these objects live quiet, isolated lives, never encountering another of their kind for millions of years on end. But ever so occasionally, Neptune's gravity pulls in just the wrong way, destabilizing a trans-Neptunian object and turning it into a comet. A ball of ice and rock that loops around the Sun, never lasting many orbits because of the intense heat of our star, evaporating material with every passage. And so out here, in the dark and the cold, these scattered worlds remain. But that is not quite the end of the solar system. The air is cold and crisp on a fresh spring night on the shores of Noordweg in the Netherlands. A young boy is sitting with his father, staring up at the clear sky, watching with amazement as a star streaks across the black. The year was 1910. The streaking star was Halley's Comet, and the young boy would go on to be the famous Dutch astronomer, Jan Oort. One of the few lucky people to spy the comet twice, once in 1910, and a second time, 76 years later, in 1986, from the window of a plane. Oort would go on to be a hugely successful astronomer, but it was comets that would be his lasting legacy, comets that took much longer than 76 years to wait for their return. It was in 1950 that Oort revived a suggestion from decades before and created a coherent, plausible theory to explain the origins of long-period comets. Unlike comets sourced from the Kuiper Belt and scattered disk, these long-period comets seem to take thousands of years or more to make a single circuit around the Sun. They also came from all directions in the sky, meaning that they clearly did not originate from a belt-like structure in the outer solar system. Since these comets could not survive for long when they came within the intense glare of the inner solar system, Oort reasoned that they couldn't have been on these orbits since its inception. There must be a reservoir, he thought, a cloud encircling the solar system in all directions that provided a steady supply of inbound comets. And so after its discoverer, this mysterious source was named the Oort cloud. Objects beyond the heliopause, sitting in interstellar space, but still weakly chained to the gravity of the Sun. However, to date, no object has actually been confirmed definitively to exist within the Oort cloud, save for the comets that occasionally make their way into the inner system. Its members are simply too far away and too small to be resolved even with our most advanced telescopes. But based on the sizes and frequencies of long-period comets, the Oort cloud likely contains roughly 5 Earth masses worth of material. As to its extent, its inner boundary is somewhere around 2,000 astronomical units from the Sun. That's 20 times further away than the heliopause. Estimates suggest that the lonely Voyager will finally encounter it in roughly 300 years. Its outer boundary, however, is unknown, with estimates ranging up to 200,000 astronomical units, or over 3 light-years, most of the distance to our nearest neighbour star. Beyond our solar system is a neighbourhood of stars, many of which formed from the same cloud of gas and dust that gave rise to our own Sun. Within a radius of 20 light-years, there are 131 known objects, including stars, white dwarfs, brown dwarfs, and sub-brown dwarfs, which straddle the boundary between the largest planets and the smallest stars. And while Proxima Centauri is currently the nearest star to the solar system, this won't always be the case, as all the stars in our vicinity, along with the Sun, are in constant motion. In addition to orbiting around the galactic center, they also move in random directions. Indeed, in roughly 1.25 million years from now, the dwarf star Gliese 710 will pass within 0.17 light-years of the solar system. Surrounding our neighbourhood of stars is a region known as the local bubble. It is, like the heliosphere, a region defined by the plasma environment of the interstellar medium. It extends for roughly 1,000 light-years on a side, and its density of plasma is roughly 1/6 of the material surrounding the solar system. Our solar system has been travelling through the local bubble for the past 5 to 10 million years. While its origins remain uncertain, most astronomers believe that a complex of clustered supernovae detonating one after the other in quick succession, pushed out this void of plasma. Indeed, remnants of these supernovae in the form of rare isotopes of iron, manganese, plutonium and aluminium have been found embedded in the seafloor and in the Antarctic ice sheet. And so, Batuta passed the millennia-long journey in silence. It monitored the changes in density and temperature as it began its first navigations through the heliosheath and out into the interstellar medium through the local bubble. It felt the sting of cosmic rays and diligently repaired the damage. It considered its long-distant ancestor Voyager 1 and its later siblings, bravely venturing out into the endless black. Behind it, the sun grew small and dim, till eventually, as far as its instruments were concerned, it became just another star. After 10,000 long years, Batuta was now plunged into the void, the great depths between the stars. Its interstellar journey had truly begun. A 100,000 years had passed since Batuta had first left the Earth, and roughly halfway through that journey, the little probe had decided to change direction. The change to this new destination, which sits 90 light-years away from the Earth, had cost it 8,000 years in its overall trajectory, but Batuta had decided it was worth it. The spacecraft was an avid student of human history, and had been poring over records, books, charts, digital files, and everything else that its creators had uploaded to its systems. And one star in particular had caught its attention: Algol, the Demon Star. 3,200 years ago, an Egyptian list of lucky and unlucky days had counted it as a star that brought bad tidings. In Greek mythology, the star represented the decapitated head of Medusa, with Perseus the hero holding it triumphantly alongside him for the world to see. And in Chinese astronomy, the star was a member of 5, representing a mausoleum. Within them was a star that roughly translates as piled up corpses. The star, of course, had a more proper scientific name: Beta Persei, the second brightest star in the constellation Perseus. But in the 17th century, its name took on a new meaning when Italian astronomer Geminiano Montanari discovered that Algol, the demon star, would eerily change its brightness. More than a century later, keen astronomers noticed that this change happened periodically. Roughly every 10 days, Algol would suddenly dim for a period of hours before returning to normal. But it wasn't until the 1800s that astronomer Edward Pickering of Harvard Observatory, who famously hired a team of women, his Harvard computers, to analyze stellar spectra, discovered the cause. Algol's dimming wasn't caused by one star, but 2. A bright, hot main star orbited by a smaller companion. And so from our perspective, when the companion crossed in front of its parent, the entire system appeared dimmer. While seemingly a simple solution, Algol's present configuration betrays a history of violence. The 2 main stars were born at the same time, and Algol A, the primary and largest star, is still in its main hydrogen-burning sequence, while Algol B, the smaller companion, is a subgiant nearing the end of its life. But this is the opposite of what should happen. Larger stars burn through their hydrogen faster, and so Algol A should be nearly dead. The answer to this puzzle is a process with the fairly dull name of mass transfer. When Algol B reached the end of its main sequence life and swelled to become a red giant, it overflowed the space between the 2 stars, allowing its companion to steal some of the hydrogen for itself, like a vampire preying on its own sibling. Algol is just one of many known systems hosting multiple stars. The simplest of these are simple binaries, either with 2 stars orbiting a common center of mass, or a smaller star orbiting around a larger parent. The most complex systems known have up to 9 stars, all orbiting around each other in complicated, intricate dances. For example, Alpha Centauri is actually a triple system. There are 2 stars that orbit closely together. Because the system is close enough to Earth, backyard telescopes can resolve the pair, with a third, Proxima, orbiting at a great distance. Other kinds of arrangements are far less stable, with their motions chaotic and unpredictable, competing for influence with each other. But Algol and multiple star systems aren't the only curiosities within our neighborhood of the Milky Way. There is no better place to see the universe than from the deck of a ship. Out on the ocean on a clear night, if the moon is waning, stars scatter across the sky like a shower of light, revealing their secrets from all sides. And this would have been even more acute in the early 1800s without electric lights aboard. So it's not hard to imagine the effect that this would have had on a young, curious mind, far from home and hungry for knowledge. Born in 1784 in Minden, then in the Kingdom of Prussia, Friedrich Bessel was not your typical astronomer. He dropped out of school at the age of 14 because of his distaste for Latin, and had gone on to apply his natural gift for mathematics to an import-export business. But this proximity to shipping and his time aboard sea vessels had sparked a curiosity in navigation, which then led him to an interest in astronomy. Before long, his natural ability was recognized when he made successful measurements of Halley's Comet. And then he had to make a choice: a relatively comfortable life in commerce or a less comfortable life as an assistant in a private observatory. He chose the stars. His target was 61 Cygni, the flying star of classical astronomy, named for the speed with which it appeared to move across the Earth's sky. He targeted 61 Cygni because he guessed, correctly, that its fast apparent motion was a clue that it was closer to the Earth than other stars, and so a good candidate to measure a distance to. But when he finally calculated the distance, it was so extreme that he had to devise a new measurement system to describe it. He could have used miles, or kilometers, or even multiples of the distance between the Earth and the Sun, but all of those conventions resulted in frustratingly large numbers, and so he created a new term: the light year, the distance light travels in a year. With this new nomenclature in hand, he could announce the distance to 61 Cygni, a neat 10 light years away. But 61 Cygni is not the nearest star to Earth, or the strangest, not by a long shot. For example, Betelgeuse. The 10th brightest star in the sky, despite its extreme distance of roughly 450 light-years away, Betelgeuse is both massive and gigantic. It weighs at least 15 times the mass of the Sun, and its diameter is almost unparalleled, over 750 times the width. If it were placed in our own solar system, it would engulf Mercury, Venus, Earth, Mars, and most of the asteroid belt. Indeed, Betelgeuse is so bloated and so distorted that it's no longer a sphere. Astronomical imaging reveals a lumpy, engorged surface that boils with the turmoil underneath it. In late 2019, the star unexpectedly dimmed, going from one of the top 10 brightest stars in the sky to ranking below 20th place. The cause of this sudden dimming was likely a plume of superheated plasma that the turbulent star ejected into space. The plume cooled, temporarily forming an orbiting dust cloud that obscured its brightness. Once the debris cleared, Betelgeuse returned to its former glory. But Betelgeuse will not last much longer. It will soon end its life, likely sometime within the next 100,000 years, exploding in a tremendous supernova. Theoretical calculations suggest that at its peak it will be as bright as the half-moon, making it brighter than every other star and every planet in the night sky. It will be a fierce point, uncomfortable to look at, producing enough light in the middle of the night to comfortably read a book by. And yet, within a matter of weeks, it will fade into irrelevance. no longer visible to the naked eye, and Orion will stand in the night sky without his shoulder. But the vast majority of stars are not giants. They are either mid-sized stars like the Sun or smaller red dwarfs. And that includes Proxima Centauri, the closest star to the solar system, a red dwarf that can only be viewed through a telescope. The star itself is rather unremarkable, except for one thing. It carries a planet with it. That planet is a small, rocky world, roughly the size and mass of the Earth, orbiting within the star's habitable zone. Thanks to an observational campaign known as the Pale Red Dot Initiative, a homage to the evocative pale blue dot image of the Earth taken when Voyager 1 was at the far edge of the solar system, we know that Proxima b, as the planet is called, is the nearest chance for life to find a home outside the solar system. As of yet, of course, there is no guarantee, as our observatories are not powerful enough to confirm the existence of life, let alone its prerequisites, such as liquid water or a stable atmosphere. To maintain habitability, planets must hug close to their parents. In the case of Proxima b, that world orbits within 0.05 astronomical units of its star, much closer than Mercury does to the Sun. That's because the light from red dwarfs is so feeble, and it's only at that close distance that a planet can receive enough warmth to cling to habitability. But if life did find a home there, it would not be an easy one. Red dwarf stars are especially temperamental, prone to star spots that can cover half their surfaces at a time, and bouts of rage that flood their local environments with electromagnetic storms of plasma. Their planets would alternate between periods of extreme cold and bursts of intense radiation. And on top of this, in all likelihood, Proxima b is tidally locked, with one face permanently pointed towards its star. This means that Proxima never sets nor rises on the planet, and half the world is locked in never-ending night, with the other always in daylight. But even this curious case does not automatically represent a dead world. Computer modelling has shown that even these planets can sustain life. The key is for there to be sufficient water and atmosphere to circulate heat around the whole planet, so that the day side doesn't roast in the glare of the star, and the night side's atmosphere doesn't freeze and catastrophically collapse. And the most fragile but intriguing case is that of the so-called ribbon world, a term coined by science fiction author Arthur C. Clarke. Ribbon worlds are only habitable in the terminator regions of the planets, the twilight zone, with the center of the day side a scorching desert and the night side a frozen wasteland. But if conditions are just right, there can be a balance between the two, opening a thin strip girdling the planet where temperatures remain stable, heated from one side and cooled from the other. And so Proxima b is just the beginning. There are an endless variety of worlds in the galaxy. At the lowest estimate, there is roughly one planet for every star, meaning that in the Milky Way alone there are at least a few 100 billion planets. On the upper end, there could be trillions inhabiting our galaxy alone. There are surely duplicates of the solar system out there, with 4 rocky inner worlds and 4 giants. There are also much more bizarre arrangements, like the TRAPPIST-1 system, which consists of 7 rocky planets all in close orbit around their parent star, 3 of which are in the habitable zone. There are giant planets so close to their stars they are actively being destroyed. There are super-Earths and mini-Neptunes. There are planets covered in thick hydrogen hazes surrounding surfaces covered in water, the Haitian worlds. There are planets so hot they are glowing, and worlds encased entirely in ice. And there are even the rogue planets, worlds with no system to call home, flung out into the black. Of course, there was no way that Batuta could ever hope to catalogue them all. And so, after its brief 10,000-year detour to the Algol system, it stuck to its planned trajectory, visiting a string of systems as the spacecraft made its way through the Orion Arm and inwards towards the galactic core. It knew that for the first million years of its journey there would be nothing much to learn. There were no signs of life or exotic breakdowns of physics to be found here. For that, it would have to reach even further, towards the core of the Milky Way itself and beyond. Mission Parameter 2. Find a way to escape the Milky Way. An internal alarm alerted Batuta. At that moment, it had just passed 1 million years since its awakening as a conscious entity. Its birthday. Currently situated midway through the Scutum Centaurus arm, the spacecraft was roughly 15,000 light-years from the core of the Milky Way. It had nestled itself near a protoplanetary disk, a ring of dusty material that was in the beginning stages of planetary formation. Batuta had stopped here several thousand years ago to prepare itself for the next stage of its journey. It had originally intended to proceed onwards as quickly as possible, but the process of planet formation was too good to ignore. Even with the eons of recorded human history before it began its journey, civilization had not yet existed long enough to watch the process unfold in real time. And so Batuta decided to wait and watch. It would prove to be worth it. The story of planet formation is the story of life. And this story begins with the raw elements that make life possible. Hydrogen, carbon, oxygen, nitrogen, and phosphorus. Without this basic quintet, life as we know it would simply be impossible. The hydrogen, of course, is the easiest. It was created in the fires of the Big Bang at the beginning of the universe, a nucleosynthetic era that for a few precious minutes converted a soup of quarks and gluons, some of the most basic constituents of matter, into a population of hydrogen, helium, and some lithium and beryllium. However, as the universe expanded and cooled from that inferno, these reactions stopped, freezing the population of light elements in its place. Scientists figured this out in the early years of development of the theory of the Big Bang, but the question remained, what about the rest of the elements? How did carbon, iron, and everything else come to be? To find this out, we will need to go back to the 1950s and to a famous scientific paper that has stood the test of time. Scientists almost never work alone. Even a single author paper will usually have several names listed in the acknowledgements section at the end, a sign that the writer had plenty of help along the way. While some collaborations for giant experiments or telescopes can stretch into the hundreds, most groups are much smaller, a handful of individuals working together on a common problem to discover something new. And so in 1957, at Cambridge University, 4 scientists gathered who would go on to change how we understood the universe forever. The paper was known as the B²FH paper, named after its authors. The B² stood for Margaret and Geoffrey Burbidge, the iconic husband and wife astronomy duo. She would later go on to discover the farthest object ever witnessed in 1974, a distant quasar, and would also find that the galaxy M87 had a supermassive black hole at its centre, all whilst fighting discrimination in astronomy. Indeed, the couple once switched job applications when Margaret was turned down for a role at the Mount Wilson Observatory due to there being only one toilet on site. Vera Rubin, another iconic female astronomer, relates the story. With their usual adaptability, Jeff, a theorist, took the Mount Wilson Fellowship and Margaret the Kellogg appointment. Not surprisingly, whenever Jeff went off to Mount Wilson to observe, Margaret coincidentally appeared. The F in B²FH stood for legendary train enthusiast William Fowler. Fowler's work would later earn him the 1983 Nobel Prize in Physics, but he once said that his greatest treasure was a gift given to him by his students and collaborators for his 60th birthday, a working scale model of a British tank engine. And finally, the H stood for the infamously outspoken physicist Fred Hoyle, who 8 years earlier had actually coined the term Big Bang Theory and would go on to be knighted for his work in astronomy. Their coming together in 1957 would show that it was stars that were responsible not only for the light that illuminates the universe, but for the forging of its elements. All stars survive by burning hydrogen in their cores, leaving behind a nuclear ash of helium. Towards the end of their lives, stars resort to burning this ash, fusing helium into carbon and oxygen. For smaller stars like our Sun, this is the end of the nuclear road, igniting in their deaths as supernova explosions. And it is those supernova explosions that are the factories with the energies needed to produce even heavier elements, filling out the rest of the periodic table. Since this landmark paper, the story of nucleosynthesis has been modified and updated. For example, in 2017, astronomers got their first multi-messenger view of a killer nova, a merger of two neutron stars. In the course of only a few minutes, a network of astronomers around the world witnessed the same event in gravitational and electromagnetic waves across the spectrum. Thanks to that event, we now understand that killer novae also contribute to the elemental population of the cosmos. But despite this, decades later, the story told by Willie Fowler, Fred Hoyle and the Burbages remains largely the same. With the death of every star, the cosmos becomes enriched, with new elements joining the swirling interstellar mix, ready to participate in the next round of planet formation. Indeed, tens of thousands of different nebulae dot the Milky Way, decorating its spiral arms like ornaments strung on a Christmas tree. No two are exactly alike, and so astronomers have taken on the habit of naming them after what they resemble, the same way you might spot an animal shape in a cloud drifting by on a lazy afternoon. Perhaps the most recognizable is the Horsehead Nebula. Located near the easternmost star of Orion's belt, it's a small subregion of a much larger complex, but it stands in stark relief as its density makes it appear black against the vibrant background. A little over 3 light-years across, the Horsehead Nebula is a region of active star formation. Its black clouds are a cocoon where newborn stars will soon emerge. Or take NGC 6537, more commonly known as the Red Spider Nebula, which sits several thousand light-years away. This complex of gas and dust is not the birthplace of a star, but a funeral pyre, the remnants of this star scattered outwards into 2 opposite regions, with each region forming thin spikes. Planetary systems begin their lives as diffuse clouds of hydrogen, helium, and a smattering of heavier elements. These clouds, known as giant molecular clouds, dot every galaxy. And it was in the early 1900s that British physicist Sir James Jeans discovered a process that would allow for these clouds to turn into stars. Jeans proposed that if the balance of a cloud was affected, then it could begin a process of runaway collapse. That balance could be disturbed by anything. However, usually, star formation is triggered in a cloud when it passes through the spiral arm of a galaxy. While spiral arms appear to dominate galaxies, they're really not that much denser than the gaps in between, containing roughly only 10% more material. The members of the galaxy, like the molecular clouds, orbit at different speeds, and so they pass in and out of the spiral arms. But when they pass through, a new round of star formation ignites, dominated in brightness by large stars, stars that die off before the cluster makes its way through the spiral arm, making the arms appear brighter and giving a galaxy its visible shape. Once a molecular cloud is set in motion, it can become destabilized and collapse, with its own gravitational pull triggering a feedback cycle. Most of the material coalesces towards the center, where friction heats it to high temperatures, becoming a protostar. The material that surrounds it spins and eventually forms a flat plane around the protostar, the beginnings of a protoplanetary disk. Much of the disk is made up of hydrogen and helium, but sprinkled throughout the swirling chaos is dust. And just like the dust that clings to the surface of your home, the dust in a protoplanetary disk sticks together. Meanwhile, as the process of planet building is underway, the protostar in the center begins to transform. Initially, it's heated from the outside in, as gas falls onto the core and slams into it. But towards the end of the protostar stage, just on the cusp of becoming a fully fledged star in its own right, it begins to heat itself from the inside out, releasing heat and energy in the form of radiation. And finally, after all the convulsions and chaos, the protostar ignites fusion in its core and settles into a hopefully long life. Within the inner regions of the disk near the young star, only the heavier elements, like iron, carbon and silicon and their molecular combinations, can survive, and so the inner regions of a solar system become the home of terrestrial, rocky worlds. But beyond the demarcation line, the glare of the young star is feeble enough over the great distances to allow ices of water, ammonia and nitrogen to remain solid. These ices mix with the dust and dirt, creating planetesimals that are far larger, and this increased gravitational pull sucks in massive envelopes of gas. The first planetesimal to form wins the gravitational prize, becoming the largest planet thanks to its ability to monopolize the gas of the disk, and so the next giants to form must fight amongst themselves over whatever is left. And these intense gravitational battles end up ejecting many planetesimals and even some planets out of the solar system altogether. In our own solar system, the giant planets formed much closer towards the Sun, where there was enough material to create their massive sizes. But as the disk cleared out, the mutual gravity of the planets pushed them outwards to their present positions. Indeed, there may even have been a fifth large planet formed along with them that was ejected during this process. Planets can even form independently of any star. The exoplanet WISE 08550714, discovered in 2014, is one such example. It is gigantic, roughly 10 times the mass of Jupiter, and sits only 7.2 light-years away from the Earth, closer than the vast majority of stars visible in the night sky. And sitting between these rogue planets and true stars are the enigmatic brown dwarfs, first identified by a team of Caltech and Johns Hopkins astronomers in 1994. Brown dwarfs are large enough to briefly sustain fusion of deuterium in their cores, but not big enough to sustain hydrogen reactions and reach the main sequence. Instead, they simply exist. To quote Universe Kulkarni from the Caltech team that discovered the first, "It looks like Jupiter, but that's what you'd expect for a brown dwarf." And so, these processes, repeating generation after generation, star after star across the nearly countless billions, fill each and every galaxy with a population of planets. And it was a delight for Batuta to patiently watch this minor miracle unfold. But no matter how much it was entranced by this event, it couldn't stay forever. Batuta had to resume its journey. And this time, it moved with purpose. It set its sights on the center of the Milky Way, through the innermost spiral arms into the dense core itself, with the sole purpose of coming face to face with the giant black hole and the distant darkness beyond. After a journey of nearly 10 million years, Batuta had finally reached the outskirts of the core of the Milky Way. The galaxy's core is an elongated bar, and the spacecraft had found itself just past the inner arm. Though getting here wasn't easy, Batuta suspected that it was not the first craft to make it to these depths. Somewhere within the Norma arm, some 5,000 light-years rimward, the spacecraft had detected a faint staccato radio signal. At first, it had suspected it was just another pulsar, but the spectral signature of the radio emission didn't match. Instead, upon further inspection, the staggered rhythm was all too familiar. It was artificial, the kind of signal that Batuta would have created itself. And so Batuta designed its own calling card, spending 10,000 years carefully manipulating a dead system so that all its rocky planets would crash into their parent star, raising the abundance of heavy elements well above what a star of its type should have. Within about 20,000 years, humanity, along with any other spacecraft in this corner of the galaxy, would notice a sudden and strange spike in heavy elements polluting this star. Perhaps they would ascribe it to some natural phenomenon, or perhaps they would assume it was the machinations of one of their wayward probes. Or perhaps they would not even notice it at all, if they were even still there. And so now, its journey so far spanning 10 million years, Batuta had finally started to feel old. But still, after everything it had witnessed and experienced, it couldn't hold a candle to the most ancient denizens of the galaxy, some of whom Batuta had had the honor of encountering. And one of those stars is known simply as Methuselah, named after the biblical character who was said to have lived for 969 years. More formally, the star is designated HD 140283, but it rocketed to fame when astronomers announced an unexpected age for it. In some estimates, it was possibly older than the entire universe, at the age of over 14 billion years. But how was this possible? Some wondered if the existence of Methuselah threatened our understanding of Big Bang cosmology. Others pondered if it called into question our most basic comprehension of stellar physics. But no matter what, Methuselah was undoubtedly ancient, and it had much to teach us. Estimating the age for an individual star is tricky. For centuries, astronomers had absolutely no idea, only that there were a great variety of stars in the galaxy. There were the middle-sized, yellow-white stars like our Sun. There were the small red dwarfs like our nearest neighbour, Proxima Centauri. And then there were the giants that came in both blue and red varieties, like Rigel and Betelgeuse, respectively. In the late 1800s, astronomers started to think that stars started out large and slowly shrank and cooled through the course of their lives, emitting light in the process. But a few decades later, Sir Arthur Eddington calculated that if this was correct, then the Sun could have a maximum age of only a few million years, a number embarrassingly out of step with the billions of years implied by geology and evolution. And so eventually, the true keys to stellar evolution came from the steady eye of Annie Jump Cannon, one of the famous woman computers hired at the Harvard Observatory and tasked with the repetitive chore of sifting through vast quantities of observational data. Hired for roughly 25 cents an hour, the computers were initially chosen as they were cheaper than the $1 it would have cost to hire men, but they would go on to accurately measure the brightness and positions of thousands of stars. Cannon herself would go on to say that no discovery is too small, for even the tiniest piece of knowledge can lead to great advancements in our understanding of the world. And her remarkable achievements were a shining example of this idea, proposing the modern stellar classification scheme that would eventually unlock the process of how stars live their lives. To begin with, the computers had developed an alphabetical scheme, but as time went on, that scheme was simplified and reordered, leaving us with O, B, A, F, G, K, or M. O being the hottest type of star, and M the coolest. Based on the work of the Harvard computers, two astronomers, Einar Hertzsprung and Henry Norris Russell, devised a clever sort of plot which compared the luminosity and temperature of a population of stars. Using that plot, they discovered that the vast majority of stars sat on a track, with a close relationship between these two properties. Today, we call this type of plot a Hertzsprung-Russell diagram, and we call that particular track the main sequence. As stars get older, they move along the main sequence, and so the main sequence tells astronomers roughly where a star is in its life cycle. Generally, stars start off dimmer and redder and tend to get brighter and bluer as they age. It is the mass of the star that determines where it starts on this track and how long it will stay on it. And if astronomers have access to an entire cluster of stars, they can calibrate the relationships between size, color, temperature, and amount of heavy elements to get an accurate gauge of the cluster's age. But this technique only works well with an entire population of stars. Determining with precision the age of a single star is a different story and extremely challenging, and Methuselah is no exception. And so the solution to the riddle of Methuselah, like most solutions to most riddles within astronomy, came down to uncertainty. Indeed, there is no doubt that the star is ancient, one of the oldest stars to exist in the galaxy. But it certainly formed well after the Big Bang. It's just a simple matter that the uncertainties associated with its age are so large that it can appear to be older than the universe itself. Indeed, despite its extreme age, Methuselah is still not the oldest possible star to still inhabit the Milky Way. That's because Methuselah is a kind of star known as a population 2 star. And to understand what that means, we have to go back more than 80 years to 1942 and an attack on American soil. The skies of Los Angeles are on fire. Sirens are wailing, anti-air raid guns are firing, and a total blackout is being ordered across the city. 1,400 shells would be spent that night as the entire population is thrown into chaos. And yet, there would be only 5 deaths, 2 from heart attacks and 3 from car accidents caused by the distraction of the artillery shells. Why? The incident would later turn out to be a false alarm caused by a floating meteorological balloon, the anxiety built up by the attack on Pearl Harbor 2 years before going off like a powder keg. Blackout restrictions would stay in place for the next 18 months to protect from attacks from Japanese submarines. However, for one clever German astronomer living in Los Angeles, Walter Baade, the blackouts presented a remarkable opportunity. Using the famous 100-inch Hooker telescope at Mount Wilson Observatory, through which Edwin Hubble had spied an expanding universe just 15 years before, Baade seized on the reduced light pollution to resolve stars around the Andromeda Galaxy, using his observations to define 2 distinct stellar populations, Population 1 and Population 2. Population 2 stars are ancient stars that have a medium amount of heavy elements polluting their atmospheres. Stars like the Sun are Population 1, with a much higher concentration of metals, the generic term astronomers use to categorize all elements heavier than helium. Though to be fair, hydrogen and helium make up more than 98% of all the elements in the universe, so it's not unfair to consider the rest of the periodic table a mere rounding error. These Population 1 and 2 stars, even Methuselah, are the inheritors of multiple generations of stars in the universe, with each generation more enriched than the previous. After every stellar death, more heavy elements forged in the cradle of supernova or within massive stars circulate in the universe, meaning that each new round of stars has a higher fraction of those heavier elements. But the first stars to appear in the universe had no heavy elements to speak of. They were as pure as they could possibly be. This generation of stars is known as Population 3. The seemingly reversed naming system a result of their proposal years after Population 1 and 2. That in turn a result of the fact that none have yet been found. We're not entirely sure how the first stars formed, but they were likely huge. This is because modern-day stars require the presence of heavier elements to moderate their fusion chain reactions, and these metals also help protostellar gas clouds release radiation, allowing them to become smaller before igniting fusion. But the first stars had neither of these advantages, so they must have formed without any metals at all, meaning that their primordial gas clouds could have stayed at enormous scales without fragmenting into smaller segments. Indeed, some models of stellar formation suggest that they may have been 100 times more massive than the Sun, while other, more exotic mechanisms find that they could have been 1,000 or even 10,000 solar masses each. Either way, at that titanic scale, they were doomed to lead short, intense lives, for with greater mass comes an increased rate of fusion reactions. At 100 solar masses or more, the first population 3 stars would have lived fast and died young, surviving only a few million years. And since those stars first arose in the dark ages of the cosmos over 13 billion years ago, the first generation came and went well before even the development of the first galaxies. The only chance a population 3 star had to survive to the present day is if it managed to enter the main sequence as a relatively small object, smaller than the Sun, and remain hidden and protected. But the chances of finding such a rare object are so slim, however, that modern-day astronomy has turned to enormous observatories like the James Webb Space Telescope to instead go hunting for their light in the faint, ancient signals at the edge of the universe. Light that was sent out when the cosmos was first forming stars and galaxies. And so generations of stars come and generations of stars go, a sequence stretching back billions of years. And while all stars share the same process of formation and share the same main sequence of hydrogen burning in their cores, different stars do encounter different final days. To begin with, for the smallest stars, the red dwarfs, they simply quietly fade into the night. They only need a relatively small amount of fusion reactions to maintain themselves, and so they glow only dimly, almost 1,000,000 times less luminous than the Sun. But because of that, they live enormously long lives, up to trillions of years before they run out of hydrogen. Medium-sized stars like the Sun, however, have a much more dramatic fate. When they first exit the main sequence, they undergo a series of rapid changes that see them swelling to become enormous red giants, then collapse again, then reignite, and back and forth. But at the end of it, after billions of years of calm, main sequence life, vicious transitions to helium burning, and chaotic spasms, all that's left of a mid-sized star is a white dwarf, the leftover core of carbon and oxygen. But when white dwarfs were first discovered in 1916, many astronomers thought that they were downright impossible, and that obviously the observers had done something terribly wrong. Sir Arthur Eddington summed up the situation when he mused about a hypothetical conversation between astronomers and the universe. The cosmos has presented astronomers with a situation where a ton of a star's material could fit inside a matchbox. The astronomical community responds to this idea with a simple retort. Shut up. Don't talk nonsense. But Ernst Erpik, an Estonian astronomer who made the first concrete observations of white dwarfs, stuck to his guns, insisting that his calculations showed that some of the stars he had measured had densities over 25,000 times that of the Sun. We know now he was right, and white dwarfs would go on to become just the first of many ultra-dense surprises that the universe had in store for us, and astronomers learned not to tell the cosmos to shut up. Despite their mass, white dwarfs occupy only a small volume, roughly the size of a terrestrial planet. Because they are the literal cores of the nuclear furnace inside a star, when they first emerge from their stellar cocoons, they have temperatures upwards of 10 million Kelvin. At these temperatures, they emit copious amounts of X-ray radiation, flooding their surrounding systems with the deadly light. But these systems are also filled with the leftover atmospheres of the stars. And what follows is a process similar to the one found inside of fluorescent light bulbs. The X-rays deliver energy to the gas, and some of that energy goes to increasing the energy level of the electrons. Those electrons then fall back down into lower energy states, and in the process release radiation of their own, this time at wavelengths much less lethal and much more beautiful. And these are the planetary nebulae. First coined by William Herschel in the late 1700s, he was mystified by their curious appearance, which to him resembled a faint, fuzzy planet. And as is usual in the profession, by the time that astronomers realized that these strange objects were the result of stellar deaths, the name had stuck. No two planetary nebulae are alike, as their structure depends on the complex intertwining of elements as a dying star heaves off its outer layers. Many of them can be viewed through a telescope, revealing a galaxy twinkling with ornaments of different shapes, sizes and colours. And adding to their beauty is their ephemeral nature. As the white dwarf cools off, after about 10,000 years it will stop emitting X-ray radiation. The planetary nebula will fade from the cosmic scene, never to be repeated again. Indeed, if the white dwarf is left alone, it too will slowly cool, but because they are so hot and so compact, they are remarkably long-lived. White dwarfs take tens of billions of years to fade to blackness, and so there are no cold white dwarfs, sometimes dubbed as black dwarfs, in the present-day universe. There simply hasn't been enough time. While most white dwarfs are typical of their kind, a few stand out. One is Janus, which has two distinct hemispheres, one dominated by hydrogen, another by helium. Another is DES J2-1474035, which is exceptionally cool. With an age of over 10 billion years, it's one of the oldest white dwarfs known, and it has a temperature of only a few thousand degrees. But if the white dwarf has a companion, it can have a much more dramatic fate. As the binary nears the end stages of its own life, it will swell to become a red giant, and if that swelling is great enough, then the material from the giant can pour onto the white dwarf. Because of the intense gravity, that hydrogen envelope can reach incredible densities, high enough to spontaneously trigger nuclear fusion. In a flash, all the hydrogen ignites, creating a nuclear blast known as a classical nova. If enough hydrogen accumulates before burning off, however, catastrophe can strike. This triggers a runaway nuclear event, with a small spark of detonation racing across first the face and then the body of the entire star, ripping it apart in a single tremendous explosion. This is a particular type of supernova, an explosion capable of outshining the combined light from hundreds of billions of stars together. Indeed, a quiet galaxy like the Milky Way only fashions a handful of these kinds of supernovae every century, and since most occur far from the Earth, we should count ourselves lucky to see them at all. But there are other types of even more energetic supernova, and they start with an extremely rare mystery in the sky. The year was 1867. The Paris Observatory was celebrating 200 years of watching the heavens, founded as it was in 1667 during the reign of King Louis XIV. One of the great observatories of modern astronomy, it is situated on a small hill on the southern end of Paris. At the time of its establishment, far enough away from the hustle and bustle of the main city that it could enjoy a pristine view of the sky, and close enough to have access to the cultural and scientific elites living further in. Indeed, Louis XIV even attempted a claim for the Paris Observatory to mark the point of the prime meridian, which also would have conveniently passed through his throne room at the Louvre. And so it was there, 2 centuries later, with Napoleon III on the throne, that 2 astronomers, Charles Wolfe and Georges Rayet, made the discovery that bears their name. They found 3 stars that showed spectral emission lines that were much broader than usual. An explanation for this strange behavior would remain elusive for decades, and one major reason for this is that Wolfe-Rayet stars would turn out to be extremely rare. Even today, with the full suite of modern astronomy available, only about 500 of these stars have been detected. And so it wasn't until nearly the 1900s that astronomers would find the truth. The spectral features were due to the presence of helium an element discovered just a year before Wolf and Rayet's observations, and an effect known as Doppler broadening. When gas gets extremely hot, its spectral lines widen due to the erratic motion of the molecules. This implied that whatever was happening with Wolf-Rayet stars, it involved a huge amount of energy. And so it turned out that Wolf-Rayet stars are so rare because they are very, very temporary. They are massive stars nearing their final days. As the outer atmospheres of these giant stars are blown away by successive red giant phases, they produce distended envelopes of gas. The high-energy radiation coming from the star strikes this envelope, exciting the gas within it and causing it to glow on its own, thus creating the strange spectral features. But what comes next is the danger, because Wolf-Rayet stars are thought to be the precursors to a supernova Type 2. Any star larger than roughly 8 times the mass of the Sun shares this grim, if spectacular, fate. Their fatal flaw is that nuclear fusion, the fundamental reaction that can power a star for eons, can't ever win in the long term against its ancient foe, gravity. Gravity is relatively weak in comparison to the other forces, but what it lacks in overall strength, it more than compensates for with patience. Quiet, incessant patience. The gravitational pull of a star's own mass is always attempting to collapse it, to shrink it into a smaller volume. Resisting that pull is the energy released from fusion, and a star can maintain that balance for millions, billions, or even trillions of years. But there is only so much fuel available in the core of a star, and once the hydrogen runs out, the star must switch to fusing helium, which is not nearly as efficient. Once the helium runs out, a massive star can instead burn carbon and oxygen, and once that runs out, it can even move on to heavier elements. But at each phase, the fusion process yields less and less energy, and so the timescales catastrophically shrink. Hydrogen burning for millions of years, helium for less than 1 million, carbon for only a few hundred years, neon for half a year, oxygen a matter of days, and silicon for only a handful of hours. And then comes iron. The crushing gravitational weight of the star pressing in, iron begins to fuse to produce heavier elements. But there is a problem. For iron fusion doesn't release energy, it absorbs it. And so with nothing left to counteract gravity, the star collapses. In only a few more seconds, the star will be dead. The pressures reach such extremes that the iron in the core converts into something strange and truly unique in the universe. The electrons are forced inside of atomic nuclei, where they merge with protons to produce neutrons. The entire core becomes a sphere only a few kilometers across, made of almost pure neutrons. The rest of the star rushes inwards towards that core at a substantial fraction of the speed of light. When it strikes, it meets a brief resistance and bounces back outwards, launching a shock wave that ripples through the remaining star's interior. But what happens next is a mystery to modern physics, despite the existence of this type of supernova being known to humanity since before the dawn of recorded history. Indeed, the earliest observations consist of simple rock carvings by unknown prehistoric peoples made around 4000 BC, and some supernovae were so bright and persistent, cultures around the world simultaneously recorded the same event. In 1054, Chinese astronomers recorded a new guest star appearing in their sky. At the same time, half a world away, the ancestral Puebloan people of modern-day New Mexico created a pictograph denoting this special event. And today, that portion of the sky is occupied by the Crab Nebula, the remnants of that mighty explosion. But in the early 20th century, the astronomer Fritz Zwicky started to deliver answers. For millennia, cultures had observed different kinds of new stars appearing. Now, thanks to the sophistication offered by modern astronomy, he could classify them. Flashes of hydrogen envelopes around white dwarfs would retain the name nova, meaning new, while these kinds of titanic explosions would be called supernova. When a white dwarf is completely destroyed, it's known as a Type 1a supernova. When a massive star meets the end of its life, it's a Type 2. And in 1987, a blast originating in the Large Magellanic Cloud made history when it became the first supernova to be detected not by looking up, but by looking down into a giant tank of water. The tank was the Kamiokande 2 detector, buried deep underground in the Mizumi mine in Japan, and it held over 1,000 metric tons of ultra-pure water surrounded by thousands of photodetectors, all super-sensitive synthetic eyes staring incessantly at the water within. Kamiokande 2 was designed to detect neutrinos, the nearly massless particles that slip through the cracks of the cosmos. Neutrinos flood the universe. There are some several trillion passing through your body right now, but they only extremely rarely interact with the rest of matter, and so for most of human history they went unnoticed and undetected. It takes enormous detector volumes, say 100,000 metric tons of water, to catch even a few. Nuclear reactions create neutrinos. The sun produces copious amounts of them every single day, and when the supernova in 1987 went off, it created roughly 10 to the power of 58 of them. Of course, the vast majority of those missed the Earth, and of those that hit, Kamiokande 2 and instruments like it were able to detect a grand total of 25 of them. But it was enough to confirm a picture that had been forming in the minds of physicists to explain how supernovae finish their explosions. The problem was that models showed that the shock front, produced when the stellar atmosphere bounces off the dense core, slows down and stalls, not able to deliver nearly enough energy to propel the explosion. But neutrinos may save the day. The conversion of iron into neutrons produces an absolute flood of neutrinos. In fact, over 99% of the energy released in a supernova goes into neutrino production. What we see is an immense flash of light, but a shadow in comparison. Of course, most of these neutrinos slip harmlessly out of the dying star, never to be seen again. But enough of them interact with enough of the star's material to reignite the shockwave, possibly allowing it to break through and destroy the star. Other mechanics, such as out-of-control resonant instabilities, similar to the kind that destroyed the Tacoma Narrows Bridge in 1940, might also play an important role. Whatever the exact mechanism, once the shockwave breaks out, it sweeps up material in front of it like an avalanche, taking a star's atmosphere and spreading it outwards at nearly the speed of light. Nuclear reactions in the material finally create the heavy elements that were attempted in the core mere minutes before, and so long after the star is dead and done, the remnants of its atmosphere remain as a slowly expanding and cooling nebula that eventually disperses into the interstellar medium. As for Batuta, the supernova caught it unawares. In the millions of years since its creation, it had grown complacent and overconfident. It had seen it all, understood it all, knew when the universe was safe and when it was dangerous, or so it thought. It had been refueling in a long-dead binary system when a sudden burst of neutrinos and gamma rays were the only warning it had before the star split itself in two and the shockwave came racing outwards. It took Batuta over 1,000 years to repair the damage, licking its wounds in the tattered remnants of the system. Grim and determined, it decided that it had spent enough time in the galaxy, and with its arrogance blown away by the White Dwarf's companion, it was time to encounter the supermassive black hole once and for all, and to leave the Milky Way behind. Batuta hung on the edge of the abyss. Sagittarius A star, the monster black hole at the center of the Milky Way, was dead ahead. The spacecraft had deployed telescopes spanning the entire electromagnetic spectrum, for this truly was a sight to behold. The struggles to get here, nearly 10 million years had passed since first leaving the heliopause gates of the solar system, were more than worth it. The environment surrounding the supermassive black hole was the most continuously energetic place in the entire galaxy. And beneath it all, under the maelstrom of plasma surrounding it and the flood of radiation emanating from near it, was the black heart itself. A horizon cutting off the interior from the rest of the universe. For a brief moment, Batuta was tempted to plunge itself beneath its depths out of sheer curiosity. Indeed, prior to its launch, humanity had not yet cracked the riddle of quantum gravity, of the way to provide a coherent, universal description of strong gravity at subatomic scales. The answer was there, in the singularity in the heart of the beast. But it was a trap. If Batuta sent itself below the horizon, it would learn nature's ultimate secret, but it would never be able to return home with the answers. And it was those same singularities, those riddles of infinity in the centers of black holes, that first cast doubt on their existence altogether. As you see, the war is kindly disposed towards me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas. So wrote German physicist Karl Schwarzschild in a groundbreaking 1915 letter to Albert Einstein from the front lines of World War I. He had volunteered at 40 and while serving in Russia had figured out the first exact solution to Einstein's general theory of relativity, solving for the case of the gravitational influence due to a spherically symmetric object. A year after that, the great mathematician and physicist David Hilbert verified that Schwarzschild's solutions broke down in the very center of the object, meaning that any attempts to describe the gravity there would yield nonsensical results. Something bizarre was going on in these calculations, something unexpected. The theoretical exploration of black holes had begun. Singularities appear in all sorts of physical theories, but can usually be explained away. For example, the force of a spring approaches infinity as the spring compresses. This singularity is not a problem, because we know that springs can't be compressed forever. Some other force, like the interaction between molecules, prevents them from getting smaller. But the singularity that appeared in Schwarzschild's solution was different. It implied that there was a region of the universe that if gravity became too strong, something happened. Something unknown. Most astronomers scoffed. Indeed, Einstein is quoted as having said, "The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality." But a small minority, like Robert Oppenheimer before he became involved in the Manhattan Project, carried on, and in 1972 astronomers came across Cygnus X1, one of the brightest sources of X-rays on the sky. The system consisted of two objects, a large, bright star and a smaller, unseen companion. Initial calculations suggested something enticing. The mass and radius of the companion made it much denser than any other known astrophysical object, dense enough to be a black hole. And so in 1975, Stephen Hawking and Kip Thorne, two pioneers of black hole physics, made a bet. They had both spent much of their careers studying these hypothetical objects and had staked their professional reputation on their reality. So if black holes did not, in fact, exist, they might just be out of a job, and so they concocted the bet as a consolation prize. If black holes did not exist, then Thorne owed Hawking a 4-year subscription to the British satirical Private Eye magazine. But if they did exist, then Hawking owed Thorne a 1-year subscription to the American, slightly less satirical Penthouse. By 1988, Hawking had paid his dues to Thorne. And with the reality of black holes came the reality of gravitational singularities. The spatial extent of a black hole is, as far as we understand it through general relativity, 0. Black holes take up no volume in space. They have no breadth, or height, or depth. They are defects, punctures in the very fabric of space-time itself. In a way, singularities are akin to subatomic particles, which also have no spatial extent. Strictly speaking, there is no width to an electron or a top quark, only ranges that define interactions with other particles, and yet they have wildly different masses. And so in one sense, all black holes have the exact same size. That is, no size at all. But they do have mass. They are composed of all the material that formed them and all the material that has suffered the unfortunate fate of falling too close to them. And black holes can and will eat anything. Any source of matter or energy is food. Radiation, dark matter, subatomic particles, clouds of molecules, entire stars, even other black holes. Anything that encroaches within the event horizon will never return to the outside universe and will always end up in the singularity. While black holes don't have any stronger gravity than usual, if you replaced our Sun with a black hole of equivalent mass, then planets would stay in the same orbits. Their unusually high densities allow them to rapidly funnel matter towards them. They can become incredibly efficient eating machines, only limited by the astrophysics of the surrounding material. But because black holes themselves don't interact except through gravity, there's nothing to stop them from getting larger, as long as they are continuously fed. The largest stars in the universe are only about 1,000 times larger than the smallest. The largest nebulae in galaxies follow the same pattern. But black holes are different. Black holes are the only objects in the universe that span multiple orders of magnitude. The smallest known black hole is currently GRO 165540, with a mass of 6.3 solar masses, but there is a slim possibility of far smaller. In the 1970s, Stephen Hawking hypothesized that the exotic, energetic, violent conditions of the extremely early universe could have flooded the cosmos with primordial black holes, with masses as small as an asteroid. But to date, astronomers have found no evidence or signature of their existence, and so scientists have focused their efforts on the other end of the mass scale, the realm of the supermassives. And there are many incredibly huge black holes that only have rough, indirect mass estimates, such as Phoenix A, which might weigh as much as 100 billion suns. But the largest black hole with a confirmed, reasonably accurate mass estimate is TON 618, weighing in at somewhere around 66 billion solar masses. Sitting 18.2 billion light-years from Earth, its event horizon wouldn't just engulf our solar system, it would dwarf it. You could travel all the way to the orbit of Pluto, a journey that takes our best and fastest probes nearly a decade to complete, and only be 1/80th of the way to TON 618's event horizon. But the closest known black hole is Gaia BH1, which is only 1,560 light-years away. However, astronomers suspect that there are many other black holes closer to our solar system. The problem is that unless they are members of a binary system, they're almost invisible. Of course, we can't see black holes directly. Instead, we can only see the material that swirls around them as it crushes into their extreme gravitational grip. But lone black holes are not accreting material like this, and so they stay hidden, lurking in the shadows. In 2023, astronomers with the Ogle collaboration announced the discovery of the first known lone wolf black hole, a 6 solar mass object sitting roughly 5,000 light-years away. They discovered it through a technique known as microlensing, where the gravity of a black hole briefly enhances the light coming from a background star. Indeed, astronomers estimate that there are around 100 million black holes in the Milky Way alone. Some are lone, some are members of complex systems, some are actively accreting, some are silent. And sometimes they collide. Black hole mergers are exceedingly rare, but they do happen. When they merge, they spiral in towards each other. The only way for them to get closer is to lose energy, and the only way that black holes can lose energy is through the emission of gravitational waves, ripples in space itself. However, gravity is by far the weakest of the known forces, and so black holes only inch together, achingly slowly. Arguably, too slowly. Indeed, physicists do not yet understand how black holes complete their mergers in less time than the present age of the universe. Dubbed the final parsec problem, after the challenges black holes face when they try to approach within a parsec of each other, it remains one of the great unsolved mysteries in modern astronomy. But black holes, ever willing to defy our expectations, do indeed merge. And when they do, there is rarely any fireworks or flash of light, unless the black holes are entrained by a ring of gas and dust that can visibly betray the event of the collision. Instead, black hole mergers are silent, a collision painted only in midnight. Their only emissions a ferocious release of gravitational waves, entire solar masses worth of energy converted into pure gravitational radiation. But the waves quickly die down as they spread out into the universe. By the time they reach the Earth, millions of light years away, the waves are barely strong enough to nudge anything more than the width of an atomic nucleus. Indeed, even though Einstein predicted the existence of gravitational waves more than a century ago, he thought that they would forever remain undetectable. But Einstein didn't know about the existence of merging black holes, and he underestimated human ingenuity. On September the 14th, 2015, the LIGO gravitational wave experiment finally struck gold. Created using lasers and a set of mirrors at its most sensitive, LIGO is able to measure a change in distance between those mirrors as small as 1/10,000th the width of a proton. As LIGO themselves state, this is equivalent to measuring the distance to the nearest star, some 4.2 light-years away, to an accuracy smaller than the width of a human hair. Despite this incredible precision, they were not planning on realizing their dream for several more years, if not decades. Indeed, LIGO had recently been upgraded, and they were running the experiment in a mode geared for engineering tests. But a tiny ripple ran through their detector, and several microseconds later through a sister detector on the other side of the continent. That ripple had an unmistakable fingerprint, the exact pattern matching the merger of two black holes. However, as awe-inspiring as these mergers are, they are incredibly rare. The nearest ones recorded are several 100 million light-years away. But there is another kind of black hole event that is just as destructive and powerful, and much closer to home. And this event involves not some ordinary, everyday black hole. No, these events involve only the greatest black holes in the universe, the supermassive ones. The first hints that the Milky Way might host such a monster came as early as 1933, thanks to the pioneer of radio astronomy, Karl Jansky. He noticed that radio emissions seemed to be extremely strong coming from the direction of the galactic center, through the constellation Sagittarius. Several years later, more detailed and higher resolution observations revealed a strong source of radio emission coming from a very compact region of that sky, which radio astronomers dubbed Sagittarius A. In the 1970s, even more detailed observations revealed that Sagittarius A was made of several subcomponents, one of which was much stronger than all the others. Robert L. Brown finally came up with a name for this interesting source, Sagittarius A star. He added the asterisk to its name because it was exciting, and in atomic physics, the asterisk is used to denote excited states. The name stuck, and very quickly astronomers realized that this might be the home of a giant black hole. Only an object with that kind of density, that kind of sheer gravitational might, could provide the energies needed to blast out a continuous strong radio signal. And after decades of work, it was observations of stars dancing perilously close to the abyss that finally confirmed it. Two teams, one led by the German astronomer Reinhard Genzel and the other by the American Andrea Ghez, developed the technology needed to follow the orbits of individual stars as they circled in real time around the monster itself. In some cases, the stars would reach peak velocities of 30% the speed of light. The motion of those stars was directly controlled by the mass of the central black hole, and the two teams were able to produce the first precise measurement of the mass of Sagittarius A star, just over 4 million solar masses, giving its event horizon a radius of around 44 million kilometers. That's over 30 times the width of our Sun. If we were to place Sagittarius A star in our own solar system, it would stretch to the orbit of Mercury, completely consuming it. But it is a dangerous game that these stars are playing. The gravitational forces near a black hole are, to put it mildly, immense. In particular, the problem is that there are strong differences in gravity across an object. If you were to fall towards a small black hole, for example, well before you hit the event horizon, you would be destroyed because the gravitational pull at your feet would be different enough from the gravitational pull at your head that you would get torn apart, or, in the appropriate scientific term, spaghettified. And outside a supermassive black hole, even an entire star cannot survive swinging too close. If it does, the black hole's tidal forces, which is the generic term used to describe differences in gravity, can overwhelm a star's own self-gravity. The star loses its own sense of identity, getting stretched and pulled into a long, thin rope of plasma that eventually makes its way down the black hole's throat. This violent tearing releases an enormous amount of energy, roughly the same amount of energy as a typical supernova. And so these total destructions of an entire star, or tidal disruption events as they are innocently termed by astronomers, can briefly outshine an entire galaxy. But a small object, like a human body, can survive the descent towards a supermassive black hole. The gravitational differences across that distance just aren't big enough to cause spaghettification. In fact, a person, or even a small spacecraft, could handily survive the pass through the black hole's event horizon. And this is because the event horizon of a black hole is not a physical boundary. There is no wall, there is no marker, there is no sign that you have just fallen off the edge of the gravitational cliff. Your only clue comes as you try to turn around and leave, and you find that no matter how hard you push your engines, how much you accelerate, how fast you go, even to the point of approaching the speed of light, you cannot escape. And indeed, once inside, your future is determined, your fate sealed. Outside the event horizon, you are free to roam wherever you please in space, but you must always march forward into your own future. Inside a black hole, however, a single point in space becomes your future. In a black hole, all roads lead to the singularity. Wherever you turn, the singularity will be right in front of you. You can only approach it second by second. In a finite amount of time, as measured by a watch on your wrist, you will strike the singularity. And when you do, you will be obliterated. And it's a relatively straightforward exercise to calculate the amount of time between crossing the event horizon and reaching the singularity. For a black hole the size of Sagittarius A star, that time is around 7 seconds. As to what you will experience at the singularity, that is something no calculation can yet reveal. We know how it will appear to you. Due to the extreme gravitational tidal effects, the paths of light get bent and warped, and so as you approach the singularity, it does not appear as a point, but as a wide, featureless plane stretching below you, as if you were landing on the surface of a black world. And of course, as you get nearer, you will become spaghettified as well, now that you are close enough to the singularity. But should some aspect of you survive, you would get a taste of the unification of gravity and quantum mechanics, the secret that every black hole hides in its deepest heart. But you will not be able to tell anybody else in the outside universe about what you have witnessed. Indeed, the only way to avoid this grim fate is to stay well away from a black hole, for there is no known force of nature that can save you once you enter. and so it was a difficult maneuver to pull off, and a dangerous one, but Batuta had spent millions of years preparing. It coasted just on the outskirts of the roaring and rotating Sagittarius A star, allowing the extreme forces of gravity to propel it to a substantial fraction of the speed of light. Stealing energy from the rotation of space itself as it went, at just the right moment, just before dipping into the event horizon, Batuta altered course, a barely perceptible shift in its momentum, and it was free. Mission Parameter 3. Find the most extreme objects and events in the universe. 40 million years of nothing. Just the grand, distant spiral of Andromeda, host of 1 trillion stars, steadily growing larger in the forward telescopes. And the Milky Way, smaller but still resplendent, shrinking behind it. Prior to leaving its home galaxy, Batuta had believed itself to be the master of time and space, accustomed to the inhumane scales that the universe operated on. But now, for the first time in its long life, Batuta felt lonely. Its sensor readings hadn't offered much distraction. Thin wisps of hydrogen and helium that bridged the 2.5 million light-year gap between the galaxies. The occasional passing cosmic ray, here and there a clump of stars to mark the presence of a dwarf satellite galaxy. This was because Batuta was swimming through a material known to astronomers as the warm, hot intergalactic medium. Its name comes from the fact that the gas has a temperature between 100,000 Kelvin, warm, and 10 million Kelvin, hot. The gas is believed to be primarily hydrogen and helium, and likely makes up almost half of the baryonic content of the universe, the other half trapped inside of galaxies. But the medium poses an extremely challenging astronomical target. It is stupendously thin and spread out over enormous volumes. This means that despite its high temperature, its overall brightness is almost insignificant, and most of our knowledge of the medium comes not from direct observations, but through computer simulations. These were scales well beyond the comprehension of its human makers, and until it undertook its voyage, Batuta itself. The universe was truly so vast it could not be grasped, only reduced to mere numbers. But now, Batuta had no such comfort. It could only wait, and wait, and wait, gliding smoothly through the near vacuum that defined the space between galaxies, observing and recording and sampling the warm-hot intergalactic medium. The only other thing that the spacecraft could count on was its founding mission: explore the galaxy and the wider universe, catalogue habitable worlds, search for extreme sources of energy, and discover a pathway to rescue humanity from its solar prison on the Earth. And so Batuta had decided that its searches must take it here, to Andromeda, a larger and more vibrant galaxy than the Milky Way, home to more exotic objects and energetic events. It would search every corner of this galaxy if it must, to find the most extreme events in the cosmos. And after several hundred years of patient observation, Batuta found just the right candidate. In 1967, Jocelyn Bell was neck-deep in her graduate studies at Cambridge University. Working under the supervision of Anthony Hewish, a pioneer in radio astronomy, Bell was convinced that she wasn't smart enough to stay at Cambridge and would be thrown out at any minute. But one night, poring over the data printouts from the telescope, she noticed, in her words, a bit of scruff. At first, this didn't seem unusual. The telescope frequently picked up radio interference or mysterious, undecipherable signals. And so Bell dutifully noted it and moved on. But a few nights later, the signal reappeared in the same part of the sky. Several weeks later, again. Rightfully skeptical, Hewish advised that they verify this potential discovery with another telescope at the array. and so at the appointed time, Bell and Hewish stood over the recorder to nothing. Nervous, Bell began to deflate. Perhaps in the end it was meaningless. But then the recorder buzzed and began printing. She'd simply miscalculated, and the strange signal appeared 5 minutes later than she predicted. Repeating every 1.337 seconds, an extremely high level of precision for an astronomical object. Jokingly, Bell named the source LGM-1 for Little Green Men. For his efforts, Hewish was awarded the Nobel Prize in Physics, while Bell, now Dame Bell Burnell, received nothing, though she would always maintain that it would demean Nobel Prizes if they were awarded to graduate students, and was more thankful that she was a pioneer for women in science. Soon enough, theorists were able to fill the gaps and provide an explanation for these pulsars. And as is often the case in astronomy, they didn't even have to invent something new. They could simply look back through the archives of the interesting, sometimes outlandish, hypothetical ideas that physicists are fond of creating when they have nothing better to do. In this case, it was a proposal from the 1930s made by Walter Baade and Fritz Zwicky, who realized that the end result of a supernova explosion was an extremely dense core made almost entirely of neutrons. A neutron star. These neutron stars would be extremely exotic, even more so than their cousins, the white dwarfs. They were denser, stranger, and more extreme. White dwarfs resist the crush of gravity through degeneracy pressure, the inability of electrons to share a common quantum state. Neutron stars also get their support through a similar mechanism, but one involving neutrons instead. And since neutrons are much heavier than electrons, they can compress together much more, allowing neutron stars to squeeze their entire bulk, typically a few times the mass of the Sun, into spheres no wider than a typical city. In essence, neutron stars are the largest known bound states of nuclear matter, atomic nuclei on the scale of kilometers. But just like the white dwarfs, they too have a cutoff mass, above which catastrophe looms. The limit for neutron stars is about 2 solar masses. Any larger than that and the neutrons simply can't support themselves and will allow gravity to win. This means that neutron stars are quite possibly the densest material possible in the entire universe, just one step away from becoming black holes. Even though neutrons are, as their name suggests, electrically neutral, a typical neutron star will maintain a small population of charged protons and electrons sandwiched in the deep layers of the interior. And the properties of nuclear material under extreme pressures cause the neutrons to form microscopic structures, sometimes forming tubes, sometimes long thin strands, and sometimes lumps. Amusingly, physicists name these different structures after various forms of pasta: spaghetti, penne, gnocchi, and so on, and give the interior structures of neutron stars the name nuclear pasta. At the outermost layers of a neutron star is a crust made of highly compressed electrons. But at the opposite end, in the core, is a substance unknown to modern physics. It could be merely some exotic state of neutron matter, or the intense pressures may force the neutrons to give way to their more fundamental constituents, a soup of quarks and gluons unseen in the wider universe since the earliest moments of the Big Bang. And in some proposals, the cores are instead made of strange matter, a degenerate state of solely strange quarks. But no matter what, neutron stars test the bounds of the exotic. The gravitational pull is so strong that light can orbit around them in a circle. The tallest mountains on neutron star surfaces are only fractions of a millimeter high. Neutron stars should also be rapidly rotating. Like a figure skater pulling in their arms to spin faster, the conservation of angular momentum takes a star's natural spin and amplifies it as it collapses. Combining that spin with a magnetic field generates an electric field, which whips up any nearby charged particles and energizes them. They then go on to generate intense beams of high-energy radiation out of the neutron star's magnetic north and south poles. But these magnetic poles don't have to be aligned with the axis of rotation, just like the Earth's magnetic field is not aligned with its spin. And so, as the neutron star spins, it carries the beam of radiation around in a circle, a gigantic searchlight circling across the sky. And if the path of that searchlight happens to pass over the Earth, we see it as a regular pulsing of radio emission. A pulsar. The pulsar discovered by Bell Burnell and Hewish rotated once every 1.337 seconds, corresponding roughly to the RPM of a record player. But that's nothing in comparison to some discovered since. The fastest known pulsar, PSR J174824446AD, rotates 716 times every second, or 43,000 revolutions per minute, faster than a jet turbine. Some pulsars even have companions, and when they do, they can be deadly. The pulsar PSR B1957+20 has another, much more ominous name: the Black Widow. This star, sitting 6,500 light-years from Earth, has a small brown dwarf companion. The powerful outbursts from the Black Widow are slowly destroying the brown dwarf. The ferocity of the attack is so much that the companion is ablating material as if it were in the direct stream of a blowtorch. And magnetars take this process to the next level. All neutron stars likely host magnetic fields, but something specific happens inside a magnetar to ramp up its field beyond the extreme. That special something likely happens at the moment of its birth, when the neutron star first emerges from the wreckage of its host star. Just like conservation of angular momentum spins up a neutron star during the period of collapse of the parent, the same thing happens to magnetic fields. If the neutron star is spinning too slowly, it won't generate enough energy to drive its magnetic fields to extreme strengths. And on the other hand, if it's rotating too rapidly, then the magnetic fields themselves become a source of drag as they are forced to move through the charged plasma still surrounding the star, acting as magnetized sails that slow everything down. But if conditions are just right, a dynamo mechanism can operate deep within the heart of the neutron star. In general, dynamos take one form of energy, usually rotational energy, and transform it into stronger magnetic fields. Indeed, a dynamo in the Earth's core amplifies our own magnetic field, and the magnetic field of a magnetar is the most powerful ever seen in the universe. For context, the Earth's magnetic field has a strength of about 1 Gauss, strong enough to nudge a needle suspended in water. Powerful electromagnetics in a supercooled MRI machine, typically the strongest magnetic fields a human will ever encounter, are about 1,000,000 times stronger. Even stronger ones can be created in the laboratory, but not for long periods of time, as the magnetic fields tend to destroy their generating machines. And so, bearing that in mind, a typical magnetar will host a magnetic field roughly 1 trillion times stronger than the Earth's. Of course, those strengths, even approaching a magnetar, is a death sentence. Neglecting the copious amount of X-rays emanating from their surface, and the beams of radiation from their poles, and the occasional flare of gamma rays, magnetic fields of this strength stretch and distort even atoms, turning them into thin needles 100 times longer than they are wide. Every and all molecular and chemical bonds cannot withstand that intensity. Even the vacuum of space itself becomes polarized when soaked with such overwhelming energy. But despite their ferocity, eventually all magnetars fade away. The magnetic fields meet resistance and slow down the rotation of the neutron star until it can no longer sustain such incredible field strengths, and the star continues on its life as a normal neutron star, or pulsar. Batuta was not easily impressed, considering all it had seen, but the magnetar managed it. It was a truly awesome sight. The radiation, magnetic field, particle count, temperature, everything, every measure of every sensor was pushed beyond its limits. There was truly nothing else like it. Except, as it gazed in wonder at the magnetar, Batuta still wanted more. Batuta was in the most fragile state it had ever been in. Over 98% of its systems were destroyed, but with what remained of its sensors, Batuta took in the magnetar before it. The explosion that had emanated from the star's surface had been a surprise, the flood of high-energy radiation unlike anything it had ever seen before. It was almost as if Batuta's musings had awakened some angry demon of old, the magnetar lashing out to show the fragile visitor what it was capable of. It was spectacular, but Batuta didn't want to stick around and risk seeing it a second time. And so, the spacecraft glided outside the solar system, putting a wide berth between itself and the temperamental star, noting in its log a definitive answer to an elusive mystery that had haunted astrophysicists for years. We will never know what the reactions were of the first people to discover gamma-ray bursts, because they were working in secret and they weren't looking for them. In 1963, the governments of the United States and the Soviet Union signed the historic Partial Nuclear Test Ban Treaty, which banned all overground nuclear tests. But despite the treaty, the US did not trust its negotiating partner and thought that the Soviets might launch secret missions to the far side of the moon and test their weapons there. And so in response to this potential loophole in the treaty, the United States launched the Vela satellites, a series of satellites orbiting well outside the Van Allen radiation belts that circle the Earth. There they would hunt for gamma rays, the high-energy radiation emitted during nuclear blasts, hoping to catch the Soviets red-handed. However, though the satellites never did see the signature of a nuclear weapon, on July 2nd, 1967, they did record a bright burst of gamma rays. The event was recorded but kept under wraps until a dozen more detections were made. Realizing that this represented more a scientific curiosity than a threat to the United States, Ray Kleber-Settle of Los Alamos National Laboratory finally convinced his superiors to release the information to the scientific community, in the process giving these mysterious events their equally mysterious name: gamma-ray bursts, or GRBs. Our sky is awash in what astronomers dub transient events. Besides the varieties of novae and supernovae, there are flares, flashes, pulses, bursts, and more all across the electromagnetic spectrum, all the way from radio to gamma rays. And these transients have been a source of wonder, fascination, and fear for millennia, well before humanity understood their exact origins. Besides the guest stars and other nova that astronomers dutifully noted in their chronicles, there were some stars that appeared to change with regularity. One of those is Mira, a red giant star in the constellation Cetus. Its name has the same root as miracle, and it was so named by astronomer Johannes Hevelius in 1662 due to its astonishing behavior. Every 11 months, it would change in brightness, a fact that appears to have been known to Chinese, Babylonian, and Greek astronomers going back to antiquity. And this is because Mira is a star teetering on the brink of extinction. It's a large star, larger than the Sun, that is fusing helium in its core. Already having lost half its mass due to its violent eruptions, a vicious cycle has begun. The outer layers of the star's atmosphere heat from the intense energy pouring out of the star, which causes them to expand. But once enlarged, the gravitational pressures on the core ease, the radiation plummets, the outer layers cool, and the star returns to some semblance of normality before beginning the cycle anew. Today, dozens of these Mira variable stars join the original in stellar catalogues. And a similar mechanism powers another class of variable star, the Cepheid variables. The simple fact that Mira and Cepheid variables can measurably change their brightness over the course of days or even hours is a matter of almost inconceivable scale. Indeed, these are entire stars, vast complexes of boiling plasma, churning magnetic fields and forges of fusion beyond human scale and comprehension that alter their appearance as easily and quickly as people change outfits. And so while we may understand the physics behind their chameleon-like nature, the energies needed to sustain these cycles still make them deserving of their miraculous names. But they do still change over a period long enough to notice, hours and days. You couldn't miss them, for example, in the blink of an eye. For something that quick, we have to turn our attention to the true transience of the universe, the rare events in the extreme ends of the electromagnetic spectrum, the flashes and bursts that come and go in a second, brief blips on a detector the only sign that something awful and violent has happened in the distant night sky. And so perhaps unsurprisingly, astronomers didn't even notice the first fast radio burst, or FRB, when it hit the Australian Parkes Observatory in 2001. Instead, it wasn't discovered until years later, when Duncan Lorimer and his student David Narkowitz spotted it in archives of pulsar data. Only 3 milliseconds long, it came from roughly the direction of the Small Magellanic Cloud. Since then, astronomers have managed to capture only 24 more of these events, ranging in duration from only a millisecond to over 3 seconds long. And whatever is causing FRBs, they are enormously powerful, putting out several days' worth of solar energy in a matter of milliseconds. Yet at the same time, they must be both rare and distant, since only our most sensitive radio telescopes are capable of detecting them. While astronomers still don't fully understand the origins of FRBs, a discovery in 2020 helped give them a major clue. Until then, all FRBs had originated far outside the Milky Way, which made their identification that much harder. But on April the 27th of that year, the Neil Gehrels Swift Observatory sent out an automated announcement that a storm of X-rays had just emanated from a known stellar remnant hiding in a distant corner of the Milky Way. That stellar remnant could have been a white dwarf, a neutron star, or even a black hole. They are all known to emit occasional X-ray flares. But this remnant was also known to emit gamma rays on a regular basis, something that astronomers suspect only neutron stars are capable of doing. Another clue came the next day, when the Canadian Hydrogen Intensity Mapping Experiment reported 2 bright FRBs coming from that same location. And over the next several days, a fleet of radio telescopes and X-ray observatories monitored several flares emanating from the source. And a picture began to emerge. A magnetar was glitching. Magnetars, like all pulsars, spin with incredibly precise timings, only slightly less accurate than atomic clocks. Indeed, the timings are so precise that they can be used for galactic navigation and wayfinding, as the famous plaque on the Pioneer probes show. Any civilization with a love for astronomy will eventually discover pulsars and measure the same rotation rate. That precision serves like a beacon. Everybody in the galaxy can agree about which pulsar you're talking about because it's so unique and so regular. But occasionally, the pulsars malfunction. Something in the crust shifts, like a titanic starquake as the ultra-dense electrons rearrange themselves, or some instability surfaces from within the complex and mysterious core. Whatever happens, pulsars can glitch, causing a sudden and abrupt shift in their rotation period. And the same thing can happen to magnetars. But when they do, that rapid glitch triggers a cascade in the magnetic field that ripples out in the form of a burst of emission across the electromagnetic spectrum, dumping a sun's worth of energy into space in the blink of an eye. Of course, Not all strange bursts on the sky lead to some cosmic disaster or explosion of energy. After the discovery of FRBs, PhD student Sarah Burke-Spoler combed through more archival data from the park's observatory and found several FRB-like events, with one notable difference. These flashes appeared to come from the entire sky, rather than being sources from one particular direction. Eventually, after an exhaustive detective search, the astronomers found the culprit. Only the park's observatory saw these mysterious signals, only in the middle of the day, and only when the visitor center was open. It turned out that they were not some new astronomical event, but rather a malfunctioning microwave in the cafeteria. But the gamma ray bursts detected in the 1960s definitely had no human source, much to the relief of the operators of the nuclear weapon hunting Vela satellites. Indeed, in time, astronomers would detect thousands of GRBs, which gave them enough data to classify them into two types: short and long, each having different mechanisms behind them. The short GRBs, lasting less than an average of a third of a second, are most likely connected to kilonovas, the merger of two neutron stars. And in 2017, astronomers were able to confirm this hypothesis when the gravitational wave of a merger event washed over the Earth almost perfectly simultaneously with the flash of a short GRB. The worldwide astronomical community sprang into action, with dozens of telescopes and observatories scattered across 6 continents continuing to monitor the event for the coming weeks. Indeed, that single event led to the publication of over 100 papers